Our second presentation is on the use of all lightweight concrete in conjunction with UHPC connection for prefabricated barrier system. And Dr. Atorod Azizinamini, our ABC UTC director, is going to do the presentation. Dr. Aziz.
All right, thank you, Armin. All right. First, before I start, like Armin said, the deadline for submitting the abstract is just next Tuesday, around the corner. So if you are interested to submit the abstract, please do so. The information that I would like to share with you, the overview of activities that we have undertaken for a couple of years to develop practical and user-friendly details for prefabricated railing system that is suited for ABC type projects. Believe it or not, in the market right now, there is no good alternative if you have an ABC project for the barrier system. And the problem is getting to be complicated because state DOTs are moving to higher levels of barrier, TL42, TL5, so, and those are big requirements. So that's why we undertook these projects, and then later the concrete industry, the lightweight concrete industry came to us, and they wanted to bank on our ongoing project and provided some very limited funds to do some tests with the lightweight concrete too. Now, I should mention this is a very preliminary work, so it's more of a proof of concept, but there is a need to do very extensive investigation because you have to do a MASH test, and we don't really have the funds to do the MASH testing. So I'll show you the overview of it. I'm not going to go to the details, but if you are interested, I will be happy to chat with you. We have actually two graduate students, I should say, Abbas Khodayari, who is working on the barrier system using the normal strength concrete, and Atif Anwar, who is PhD students who is working in the barrier system with the lightweight concrete. So I won't preach to the Pope here. Everybody knows what the purpose of the basically barrier system is, to provide the safety in our highways. And I also need to mention that we are working basically this project, even though we didn't provide any funding for Midwest Roadside Safety Facility at the University of Nebraska-Lincoln, my good friend Ron Fowler and his group, but we basically in these projects we have worked very collaboratively together. And I used to be a faculty at the University of Nebraska-Lincoln for 20 years before I moved to FIU. So I physically left UNL, but my heart still is there. So we work very collaboratively, and we have a very good relationship with the folks at the UNL. So what we need really, what we need in the case of the barrier system that is suited for the ABC type project, we want to make sure that we are not building a Swiss watch. So by that, what I mean, Murphy's Law really holds. Anything that can go wrong will go wrong in a construction project. You have to anticipate that you're going to have challenges with the tolerances. Things are not going to be perfect in the field. So you gotta take that into account in development of any type of a detail. We have to worry about the durability aspect of it, because if you have a prefabricated elements attached together with the joints, you know what happens. The more joints you have, the more service life and durability problems you have. So you got to make sure that you address that. That is a major challenge, and we have to make sure that is addressed. We also have to address for example, let's say super elevations, the curvatures, and all other details that's associated, and of course the safety on top of that. Okay. There are some there are some alternatives out there right now, but the challenge is that the alternatives that are out there is they don't accommodate very large tolerances. And like I said, we need to make sure that we are not building a Swiss watch. We have to take into account the workmanship, the people who work in the job site, the things that can go wrong weather-wise, and so on. So you have to provide, at the end of the day, basically what I call a user-friendly system. So what we did, this is a very original idea. We were just playing around with it. We said, all right, let's use first of all UHPC. No, you don't have to use a UHPC all the time. I mean, you can use other material, but we decided it's okay. Let's use UHPC. One of the main reasons for UHPC use is that the tension development length in the case of the UHPC is very small. So whatever connection that you have, if you want to splice the reinforcement or whatever you have, the splice length is going to be short, so that joint region is going to be small. Number two, and more importantly, is the fact that it's very durable. So the rapid coloride permeability in numbers in terms of the Coulomb that you deal with the UHPC is very low. I mean, in order of the 50 Coulomb, 20, 50 Coulomb, compared to, let's say, 4,000 or 5,000 that you may see in a normal stiff concrete. So very durable, nothing penetrates through these things. Okay, and then you don't have a large aggregate, so things flows. So it's a very flowable. You don't need a vibration, and you can build a dam, and you can do really lots of detailing that is not feasible with the normal stone concrete. So there is lots of advantages. So what we did here, this was our very first idea. We said, okay, let's have a stem. I hope that you guys see my mouse moving around here. So we said, okay, let's use the stem so that holds it. Okay. Actually, what proved that this stem is not big enough to keep the vertical element stable while we are building a dam and then trying to fill this thing with the UHPC. So we learned lots of lessons from here. The other lessons that we learned is that, I mean, in this case, you have to form the backside of it. Now, imagine in a real bridge, what do you have? You have, if you want to form the backside of it, the backside of it could be exposed to a very, could be hundreds of the feet from the roadway below. So it's not that easy to form the backside of it. So a couple of lessons I've learned from here was that, first of all, it was feasible with UHPC to connect these two things. This stem was not good enough to keep things stable. And then this may not be perfect thing to accommodate the super elevations and the curvature and things like that. So, but nevertheless, this was a good starting point. And here you can see some dimensions. Really, some of the reinforcement comes up from the deck, and then you splice it basically with the reinforcement that comes from the vertical element and so on. So we casted and tested a couple of specimens. One specimen was just completely simulating the cast in place, okay, and one of them UHPC. Now, I must say, we only did the static testing, okay. We did not do any kind of a mesh testing. One of the biggest questions that somebody can ask, and very rightfully so, this is a component testing. So one of the questions that can be asked is, what is the relationship between a component static testing and a mesh test? To give you the answer, we really don't understand that relationship yet. There are some ongoing work, especially at Midwest Roadside Safety Facility, that they're trying to shed some light to that, but we do not know the answer yet. Nevertheless, this static test qualitatively gives you some idea. The other thing is that we use the very the width of this specimen in that direction was small, about 3-4 feet. And so the question is that, okay, how does that simulate? Because that doesn't, if I apply load over here, that really doesn't allow the formation of the yield line that we designed this barrier system with. That really, so that's another question. So this specimen could be far away from providing us exactly the same picture of the performance that we would expect if this detail was used in a real project and it was subjected to a, let's say, truck hitting basically the barrier. Nevertheless, it provides some comparative. So we tested a couple of specimens, one with basically everything with just cast in place, and the other one with the UHPC. Now, when you do a UHPC, what you have to do, you have to make sure that the surface that is in contact with the UHPC has an exposed aggregate. So there are very good references on that of how you should do that. You have to use a sandblasting, basically. Use a sandblasting to make sure that the surfaces that come into contact with the UHPC, it has an exposed aggregate. You got to make sure that 24 hours before you cast the UHPC, you have basically you moisturize the surfaces, because the water content, water cementitious ratio in the case of the UHPC is very low. I mean, you're looking at the 0.18, 0.2. And if it's the surfaces that come in contact with UHPC is dried, it will suck that moisture from that little water that's in the UHPC, and it will cause a shrinkage. So you got to make sure that those two issues are addressed. What we saw basically in the case of the UHPC, and this is something that we see from almost all other UHPC-based solutions. Any region that has a UHPC, there is no mode of failure. There is no failure that takes place in those regions. That UHPC, really, the way you should look at it is that if you have a region with the UHPC, it's like having let's say, concrete attached to a piece of steel. That's really bottom line is. The UHPC is so strong. I mean, this is a 22,000, 25,000 PSI compressive strength, and the tensile strength, I mean, is about 1.2 KSI. But that region basically is eliminating any kind of possibility of the damage in this area. So you're going to be shifting the damage either up or below that UHPC area. And we saw fairly comparable actual behavior between the two specimens, one using a cast in place, one using a UHPC. So this was a good piece of information that we obtained. And of course, Abbas and Atif, they've done lots of good work and do numerical analysis with a nonlinear finite element analysis, trying to develop a model that is calibrated with the test data. And the purpose of that was to conduct a parametric study. And I'll show you later on how we use those parametric study. Now, later what we did, we said, okay, remember that I said that we had a big stem over here and then this was a flat area. And then the purpose of that was to keep basically the vertical element stable while we put in the UHPC. Then what we said, you know, we need to have a detail, first of all, that we don't have to form the backside of it. And number two, the vertical element is fairly stable. So what we did is created a cavity in the deck, basically. We said, okay, when you cast the deck, just put them using there are a number of ways that you can do that. When you cast the deck in the ABC projects, you make sure that there's a cavity at the end, and then the reinforcement comes out. And then the reason for this reinforcement extending over here is because to have a over tension splice length and then develop these bars. Actually, what we are finding out that there is no need even for that one. Okay, that's a different questions that we need to address. And so in this case, the vertical element comes in and then sits right on the top of the deck. Now, we put some kind of a shim here, and we are also thinking about putting a adjustable bolts over here so we can adjust the elevations of it. We've got another detail actually is even probably is a little bit better than this one. I don't have that detail, but I think that is going to be even more practical. You don't need the cavity, but you will have a layer of UHPC over here, and then you will have basically bolting the vertical element to the deck. But in this case, basically you fill this thing with the UHPC over here, and then once you have it, then you place the vertical element. The purpose of this little gizmo that you see down here, okay, you can guess it. If I have it just a little bit of it, maybe even a washer, if I put on the edge, and I put this thing, this little stem that you see is going to push the concrete out, and it's going to make sure that this, when you place this vertical element on the deck, this thing is basically having a very seals off this area. So that will address a durability problem. That will make sure that the entire vertical element is in contact with the deck. Okay, and basically in this case there is no need to form the backside of it. So this detail is a very interesting detail. So what we did is we made a very narrow specimen just for constructability, and we wanted, without any testing, we said, okay, let's do this thing and then let's see if this detail is feasible, and worked very nicely. We had several other alternative. Now let me come back to if you remember, we used a very narrow test specimen. Okay, now if you have a joint in the barrier, which we do in the prefabricated, if the vertical element is going to be prefabricated, guess what? I mean, you're going to have some joints, the adjacent units of the barrier have to be contacted to each other. So the critical loading actually is not in the loading in the middle, but it's going to be at the edge of it actually. And then the other thing is that this shape is not really like a V shape; it's more like a trapezoidal. Okay, so and we've verified this and what kind of boundary condition. We've done lots of work trying to. I won't go too much to details of it, but you can. We've done lots of work trying to see that where it should be loaded, where use the numerical analysis. What should be the width of the width? When I say width, means that this length right over here. How wide this test specimen should be, what kind of boundary condition we should have, and so on. Again, keep in mind, these are a static testing. What is the relationship between a component, the static testing, and a MASH test? Because when you do a MASH test, you have a passenger car, you have a light trucks, and then the heavy trucks. And depends on what level of the testing that you do. Okay? What is the relationship between the static test and the MASH test? That question is not completely answered. We know some answer to that, but there's ongoing work in Midwest Roadside Safety to shed lights on that. So Abbas and Atif have done lots of neat work over here, and what we are seeing really, if you load it in the middle, the yield line pattern is more like a trapezoidal, not the basically the V shape, and that is being recognized, and some of the AASHTO criteria is being modified. And then the other thing is that the level of lots of state DOTs are moving TL42, TL5. Okay, these are really heavy loads. Okay, the requirements. So the other thing that we have really zoomed in is that really, first of all, you need to have certain width. Right now we are concluding that this dimension could be about 15 feet. You'll be fine. And then the edge loading actually is more critical. The edge loading is very critical. What we are finding out is that the ultimate capacity for all specimen was below 80. There is a requirement that basically that you have to be, let's say TL42, you have to be reaching 80 kips. We are finding that you are not reaching that, even with cast in place. Doesn't matter, cast in place. And this is actually using a very number 6 bars in the deck. So that is a problematic. That's something that needs to be looked at. Okay, that is not. Now again, these numerical models that we have analyzed needs to be basically verified further, maybe, and we plan to work very collaboratively with Midwest Roadside Safety at UNL. So we are working jointly, trying to see that we are not daydreaming, or if this is true. If true, then we have to do some modification to the AASHTO requirements. Our results show that in the edge loading, basically this is a yield pattern if I use a cast in place and if I use a UHPC. So very similar yield pattern. This is a connecting with that second connection that I showed you, basically. So moving on. So we have actually constructed one test specimen that we're going to be testing as an edge loading, 15 feet wide. And this is a specimen. And let me see. Armin, could you tell me how much time do I have?
Dr. Azizi, I think we need to wrap up.
Okay, all right. So this is a specimen I'm showing you that we have basically right now constructed. Okay, we have sandblasted. This is a 15 feet specimen that I showed you. This right here is a schedule for testing. All right, that's the end of it. Armin, thank you.
Thank you very much, Dr. Azizinamini. As always, very great presentation and great product. If there is any questions, you can ask during other presentations, or you can ask directly Dr. Azizinamini or myself. I will take it to Dr. Azizinamini.